July 21st, 2024. Everything we thought we understood about the red planet changed in an instant. On that day, the precision drill of NASA's Perseverance rover bit into the surface of a rock officially designated Chayava Falls, cutting through billions of years of Martian silence. What the instrument exposed in those first moments caused NASA to call an emergency assembly of its most senior scientists. The images transmitted back to Earth showed dark spots arranged against a pale background, a pattern researchers immediately recognized: leopard spots. Small, distinct, arranged with a geometry that defied simple geological explanation. On Earth, formations like these point to one thing and one thing only: traces of ancient microbial activity preserved inside rock across enormous stretches of time. And now, impossibly, the same formations had appeared on Mars. For decades, humanity has poured billions of dollars, millions of hours of engineering effort, and the lifetimes of countless brilliant minds into the search for signs of life on the red planet. We have allowed ourselves to dream, to theorize, and sometimes even to hope. But now the contents of a single Martian rock have begun transforming years of careful speculation into something far more electrifying, something that sits uncomfortably close to confirmed reality. Perhaps after all this time, after all this searching, we have finally found what we have been looking for. To understand why this discovery is so significant, why scientists around the world paused their work and leaned forward in their chairs when those images arrived, we have to begin at the beginning. We have to understand the landscape, the history, and the extraordinary chain of events that led a six-wheeled robot to drill into the right rock, in the right place, at what may prove to be exactly the right moment in human history. Jezero Crater is a wound on the surface of Mars. It stretches approximately 28 miles in diameter, a vast circular depression that dominates the landscape of the planet's northern hemisphere. Stand at its rim today, and you would see nothing living. The soil is rust red and bone dry, blasted by ultraviolet radiation that scours the surface with relentless intensity. The thin atmosphere, less than 1% as dense as Earth's, offers almost no protection from the sun's charged particles. At night, temperatures plunge to levels that would kill an unprotected human being in minutes. Jezero, in the language of the present, is a dead place. It looks like the surface of a world that never knew warmth, never felt rain, never hosted the stirrings of chemistry that could become life. But language can only describe what we see in the present, and the present is not where the story lives. Rewind the clock by 3.5 billion years. The scene transforms completely. The silence shatters. Jezero Crater, in that ancient epoch, was a place of chaos and energy and movement. A massive river wide, fast, and loaded with sediment broke through the northern rim of the crater and poured its contents inward. Billions of tons of water surged through that breach over millions of years, carrying mud, dissolved minerals, and organic compounds torn from the surrounding highlands. The river slowed as it reached the crater's interior, dropping its sedimentary load across a broad delta, building layer upon layer of material that settled like pages in an archive. The crater filled, slowly but steadily, becoming a lake. A genuine liquid water lake, sitting open beneath an early Martian sky that was thicker than the one we observe today, warmer, more sheltered. That lake was not still water. It was alive with chemistry. Minerals dissolved in the water created gradients of concentration. Heat from geological activity, Mars was far more volcanically active in its youth-warmed portions of the lake floor. Carbon compounds circulated through the water column. The conditions that existed in Jezero Crater 3.5 billion years ago were not merely hospitable to life. By every measure science currently possesses to evaluate habitability, they were the kind of conditions that, on Earth, reliably produced life. This is why Jezero was chosen. This is why the engineers and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, spent years arguing for this location as the landing site for the Perseverance mission. Every other candidate site had arguments in its favor, but Jezero had the river delta, and river deltas, on Earth and presumably elsewhere, are the most effective natural archivists on the surface of a planet. When sediment-laden water slows and drops its load, it buries whatever is carried with it. Organic molecules, microbial structures, chemical signatures, all of it gets sealed into layer after layer of compressed rock. The process acts as a kind of geological filing system, sorting material by time. The deeper you drill, the further back you reach. River deltas on Earth have preserved biological evidence going back billions of years. They gave us some of our oldest confirmed fossils, some of our most ancient chemical signatures of life. If Mars ever hosted life, a crater lake with a river delta feeding into it was exactly the kind of place where evidence would be entombed and preserved. Today, the Perseverance rover moves along what was once the floor of that ancient riverbed in a region NASA scientists have designated Neretva Vallis. The rover is small by human standards, roughly the size of a compact car, but it carries an instrument suite that represents the absolute frontier of analytical technology. It can examine rock chemistry at scales far smaller than a human hair. It can identify organic molecules with a sensitivity that would have seemed fantastical to scientists even a generation ago. And it is slow, methodical, and patient in the way that only a machine can be patient, moving through the landscape one careful meter at a time, photographing, analyzing, drilling, and waiting for commands from a team of engineers and scientists hundreds of millions of miles away. But to reach the rocks that contain the most ancient and most pristine records, Perseverance had to accomplish something that nearly ended the mission entirely. The path toward the most scientifically promising section of the ancient delta took the rover through a field of sand dunes. These were not small obstacles. Martian dunes, shaped by a different gravity and a different atmospheric density than Earth's, can form configurations that are genuinely treacherous for wheeled vehicles. The rover's wheels, designed for hard rock, struggled on loose granular material. Engineers at JPL watched telemetry data with the particular concentration of people who know that a single bad outcome cannot be undone by a second attempt. The rover spun its wheels on steep slopes. It consumed time and power working through terrain that, on Earth, a person could walk across in minutes. For weeks, the mission hung in a state of suspended tension. The destination that justified all of this effort, all of this engineering ingenuity, all of this anxiety, was an area the science team had named Bright Angel. The name is almost ironic. The place is not peaceful. Even by Martian standards, which are extreme by definition, Bright Angel looks alien. Pale rocks rise against the red desert like bones pushing through skin. These are not surface rocks, not boulders deposited recently by impact or erosion. They are exposed layers of the ancient lakebed, rocks that have not seen direct sunlight for an unimaginably long time, rocks that were laid down when Mars was a different world entirely. When Perseverance finally reached Bright Angel, the engineering team breathed something that was not quite relief because the real challenge was just beginning. The rover's cameras began their systematic survey of the exposed rock faces, processing image after image, transmitting data back to Earth across a communication delay that meant every exchange took minutes. Scientists on the ground pored over each new image, looking for anomalies, for patterns, for the kind of visual signature that would mark a sample as worth the precious time and resources required to drill. And then, among the hundreds of gray and rust-colored fragments that littered the landscape, the cameras found Chayava Falls. The rock's formal designation does not capture what made it different. What set it apart were the white veins that ran through its surface mineral deposits of calcium sulfate, the same compound found in gypsum, a substance that on Earth forms only in the presence of water. These veins were like a signature left behind by the ancient lake. They said, water was here. Water moved through this rock. Water carried minerals and deposited them in these channels. And if water did all of that inside this rock, then this rock was present during the period when Jezero was wet. It was a witness. And Perseverance was about to ask it to testify. The rover's drill engaged. The mechanism is precise and powerful, capable of cutting into rock that has survived billions of years of geological pressure. As the drill turned, it carved a circular channel into the surface of Chayava Falls, removing material and exposing the interior that had not been touched by the Martian environment since the planet's wet era ended. Fine dust rose and settled in the low gravity. The drill withdrew. The cameras moved in. Mission control in Pasadena fell silent. The interior of the rock, freshly exposed, showed something that did not fit easily into any geological explanation. Against a pale, cream-colored background of mineral material, dozens of small dark spots stood out with extraordinary clarity. Each one roughly circular, each one only a few millimeters across, no larger than a poppy seed, as one scientist would later describe them, and each one surrounded by a border of slightly different color that sharpened the contrast between spot and background. The pattern was immediately, undeniably familiar to everyone who studied the image. Leopard spots. The same formations seen in some of Earth's oldest rocks, in sedimentary layers laid down billions of years ago when our own planet was young and microbial life was just beginning to establish its first foothold. The same pattern that, on Earth, is formed through a specific biological process, a process that requires living organisms to produce. The discussion that followed in Mission Control was not casual. It was not the kind of excited chatter that accompanies a novel but explicable discovery. It was the careful, cautious, intensely serious conversation of scientists who are looking at something they know might be genuinely important and who also know that the history of astrobiology is littered with exciting observations that turned out to have prosaic explanations. The stakes were too high for anything less than absolute rigor. The implications of these spots, if they were what they appeared to be, were too enormous to approach with anything other than the most disciplined skepticism. Because what those spots might represent, what they represent on Earth without exception, is the chemical residue of life. To understand why these small dark marks on a Martian rock could be so significant, we need to go deep into the chemistry of life itself. Not the complex, macroscopic life we see around us every day. Not plants, not animals, not the visible world of biology, but the invisible, ancient, foundational chemistry that underlies every living system that has ever existed on Earth and possibly elsewhere. Life, at its most essential, is a process of controlled chemistry. Every living organism, from the simplest bacterium to the most complex multicellular animal, fundamentally exists to manage a flow of energy. Organisms capture energy from the environment, from sunlight, from chemical reactions, from heat, and they use that energy to build and maintain their internal structures, to grow and to reproduce. The details vary enormously across different forms of life. But the underlying principle is always the same. Life is a chemical engine that extracts energy from its surroundings and uses it to maintain order against the universe's natural tendency toward disorder. On Earth, the earliest life forms could not photosynthesize. The complex biochemical machinery required for photosynthesis took billions of years of evolution to develop. The first organisms had to obtain their energy through different means, and the most primitive of these means involved a class of chemical reactions known as redox reactions, reduction and oxidation reactions, which involve the transfer of electrons between chemical compounds. Try to imagine this process as a kind of microscopic, very slow, very controlled fire burning inside the rock itself. When we burn wood or coal, we are running a rapid oxidation reaction. Carbon-based material reacts with oxygen, releasing energy as heat and light. Early microorganisms could not build an open flame. They did not need to. Evolution, working through billions of molecular accidents and selecting for whatever worked best, found a way to extract energy through the same fundamental chemistry, but at a pace and a scale that could be controlled and harnessed at the level of individual cells. These ancient microbes found organic carbon in their environment. Carbon compounds deposited in sediment, dissolved in water, incorporated into minerals. They ran chemical reactions that effectively burned this carbon, breaking chemical bonds and capturing the energy released by that process. The energy produced through this biological combustion powered the cell's internal machinery, the synthesis of proteins, the copying of genetic material, the construction of cell walls, the movement of molecules across membranes. All of the work of staying alive. And as a byproduct of this process, as the chemical equivalent of ash left behind after burning, the microorganisms left a specific signature in the rock. The redox reactions they ran preferentially concentrated certain minerals and depleted others. They converted compounds of iron from one oxidation state to another, producing magnetite and hematite iron minerals with distinctive dark coloration. They mobilized phosphates, concentrating them along the boundaries of the zones where microbial activity was highest. And they created, in the rock surrounding each active microbial colony, a distinct chemical environment that contrasted sharply with the surrounding, unprocessed rock. The result, preserved in stone across billions of years, is exactly the pattern that Perseverance photographed inside Chayava Falls. Dark spots, light background, chemical gradients at the boundaries. A pattern that encodes, in the language of mineralogy, the story of organisms that lived and fed and built their microscopic structures in a Martian lake bed, then died as the lake dried, and left their chemical shadows behind in the rock. Each of those spots, if the biological interpretation is correct, is the preserved trace of a microbial colony. An empty plate, as one scientist evocatively described it, left behind after a feast that took place when Mars was still a living world. The microbes are gone. The water that sustained them is gone. But the chemical signature of their existence, the specific recognizable pattern of their chemistry, has survived for 3.5 billion years, sealed in stone, waiting. But science does not accept interpretations on the basis of appearance alone. Pattern recognition, no matter how compelling, is not confirmation. The history of science includes too many cases of patterns that seemed meaningful and turned out to have purely physical explanations. The famous case of the Martian meteorite ALH 84001 is a cautionary tale that every astrobiologist carries with them. In 1996, NASA announced what appeared to be fossilized microbial structures inside a piece of Mars that had landed in Antarctica. The scientific community was electrified. Then, over years of follow-up analysis, the consensus shifted the structures were likely produced by non-biological chemical processes. The excitement was real. The evidence, ultimately, was insufficient. So when Perseverance transmitted those images of the leopard spots inside Chayava Falls, the science team did not declare victory. They deployed every analytical tool at their disposal to interrogate the rock with the kind of rigor that could either confirm or demolish the biological hypothesis. This was not a moment for excitement. It was a moment for science. The primary analytical instrument aboard Perseverance that rose to meet this challenge is called SHERLOC Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. The name is deliberately evocative. Like the fictional detective, Sherlock's purpose is to find what is hidden, to look beyond the surface, to identify the truth that careful observation can reveal. It works by directing a precisely tuned ultraviolet laser at a target and analyzing the way the light interacts with the molecular structures of the material. Different molecules scatter the laser light in different characteristic ways, producing spectral signatures that function like molecular fingerprints. SHERLOC can identify specific organic compounds' carbon-based molecules at concentrations and scales that no previous Mars instrument could approach. When SHERLOC was trained on the surface of Chayava Falls, and when the results were processed and transmitted back to Earth, the room at JPL went very quiet for a different reason than before. The data confirmed the presence of complex organic molecules, carbon-based compounds structured in ways that pointed toward biology, were present in the rock. And they were not distributed randomly throughout the sample. They were concentrated. They were found most abundantly, most densely, inside the boundaries of the dark spots, the leopard spots themselves. The spatial correlation between the visual pattern and the chemical signature was precise. The molecules were where the biology, if there was biology, would have left them. This is not, the scientists were careful to emphasize, direct proof of life. Organic molecules can be produced by non-biological processes. Meteorites carry organic compounds. Certain geological reactions can produce carbon-based molecules without any biological input. The presence of organic chemistry in a Martian rock is extraordinary and significant, but it is not by itself sufficient to conclude that living organisms were responsible. What elevated the significance of the SHERLOC data was the confirmation from a second instrument, the PIXL scanner, the planetary instrument for X-ray lithochemistry. PIXL works differently from SHERLOC. Rather than identifying molecular structures through laser spectroscopy, it maps the distribution of chemical elements across the surface of a rock at extremely fine spatial resolution. It produces, in effect, a chemical map, a picture of where each element is concentrated and where it is absent. The PIXL data produced something remarkable. At the boundaries of the dark spots, at the precise locations where the organic molecules were concentrated, there were corresponding concentrations of specific minerals. Iron compounds in the form of magnetite and hematite, and phosphate minerals. The chemical geography of the rock matched, with extraordinary precision, the signature that biological redox chemistry would be expected to produce. On Earth, when microorganisms run redox reactions in sedimentary rock, they leave behind iron minerals and phosphates at the boundaries of their active zones. Geologists studying ancient terrestrial rocks from the Pilbara region of Western Australia, for example, some of the oldest sedimentary rocks on Earth find exactly this combination of features. Dark spots, organic concentration at boundaries, iron mineral deposits, phosphate enrichment. These features, taken together, constitute what astrobiologists call a biosignature, a chemical pattern that is so specifically associated with biological activity that its presence in a geological context is considered strong evidence for biology. The combination of features found in Chayava Falls is not one or two of these indicators. It is all of them simultaneously in the same rock, in the same spatial locations, in the correct relative concentrations and configurations. The probability that all of these features could be produced simultaneously by purely geological processes, and that they would all be found together in a single sample from a river delta that was actively flowing when Mars was at its most habitable, defies casual dismissal. The team that analyzed the Chayava Falls data described their findings with the kind of careful, measured language that characterizes serious scientific communication. But the substance of what they said was extraordinary. Never before, they indicated, had such a comprehensive and internally consistent set of potential biosignatures been identified in a single Martian sample. Not in 30 years of Mars exploration, not across the dozens of missions and thousands of analyzed images and rock measurements that had been accumulated since the first spacecraft arrived at the Red Planet. Chayava Falls was different. And yet, Mars, this most frustratingly mysterious of planets, was not done complicating the picture. The same rock that produced the most compelling biological signatures ever found on another planet also contained a feature that raised an uncomfortable alternative hypothesis. Running through Chayava Falls, cutting across the ancient sedimentary layers in a pattern that could not have been deposited at the same time as the lakebed sediments themselves, were white veins. Calcium sulfate veins. The same mineral deposits that had originally attracted the science team's attention. These veins are younger than the surrounding rock. They formed after the lake dried when water, a different, later episode of water, percolated through fractures in the rock and deposited minerals as it evaporated. And this later water event introduced a complication. If water flowed through the rock after the biological activity would have occurred, could that later water have introduced the organic molecules that SHERLOC detected? Could the chemical signatures that looked so biological actually be the result of late-stage non-biological fluid chemistry? This question, one that the science team identified and grappled with openly in their published analysis, is not easily dismissed. Mars has a long and complex geological history, and that history includes multiple episodes of water activity at different times and under different conditions. The veins in Chayava Falls are evidence of one of those later episodes. The organic molecules detected by SHERLOC are present near those veins. The spatial relationship between the two is close enough to be potentially significant. The researchers spent months analyzing this question. They looked at the isotopic composition of the organic molecules, the specific ratios of different forms of carbon atoms, which can sometimes indicate whether compounds were produced biologically or through inorganic chemistry. They studied the spatial distribution of the organic compounds relative to both the dark spots and the mineral veins, trying to determine which was the better predictor of organic concentration. They compared the mineral assemblages in the veins with what would be expected from purely geological fluid chemistry. The results did not resolve the question with finality. Science rarely produces that kind of clean, unambiguous answer, particularly when working with samples that are billions of years old and have been subjected to multiple overprinting events across geological time. What the results did produce was a probability assessment. The biological hypothesis, the researchers concluded, was not merely consistent with the data, it was favored by the data. The specific combination of features, their spatial relationships, their chemical compositions, and their geological context collectively pointed more strongly toward biology than toward any identified non-biological mechanism. This is the position of the scientific community regarding Chayava Falls as of the most recent published analyses, not proven, but strongly suggested. The most convincing potential biosignature yet found on another planet, assessed by the most rigorous methods currently available, leaning toward life. The weight of that assessment is enormous. Consider what it means in the context of the history of Mars exploration. The first missions to Mars, the Mariner flybys of the 1960s, returned images of a cratered, apparently lifeless surface that shocked scientists who had expected something more Earth-like. The Viking landers of the 1970s touched down and conducted the first chemical experiments on Martian soil, looking for signs of biology. The results were ambiguous in ways that have fueled scientific debate for 50 years. Subsequent missions, the Mars Pathfinder, the Spirit and Opportunity rovers, the Curiosity rover, progressively built a picture of ancient habitability, confirming the presence of ancient water, identifying mineral deposits consistent with long-term lake environments, and detecting organic molecules in the soil. Each mission advanced the story. Each one moved the needle closer to the answer. But none of them produced what Perseverance produced inside Chayava Falls: a spatially coherent, chemically multi-layered potential biosignature in a single sample from a location that was, by every geological indicator, exactly where life should have been if it ever existed on Mars. The science team that published the Chayava Falls findings was unambiguous about the significance of what they had found, even as they maintained appropriate scientific caution about interpretation. They stated that this discovery represented the most compelling and complex suite of potential biosignatures ever identified in a Martian rock. They acknowledged that alternative explanations could not be ruled out. And they called for the sample to be returned to Earth, where the full analytical power of terrestrial laboratory science could be brought to bear on the question before any final conclusions were drawn. That call for sample return is itself significant. It is the scientific community's formal acknowledgement that the question raised by Chayava Falls is too important, and the potential answer too consequential, to be resolved by instruments operating remotely on another planet. The question demands the best analysis that human science can provide. And the best analysis that human science can currently provide requires the rock to be here on Earth, where it can be examined by every technique available in laboratories around the world. The Mars Sample Return Mission, the planned joint endeavor between NASA and the European Space Agency, is designed to retrieve the samples that Perseverance has been carefully collecting and caching throughout its mission. The samples are sealed in titanium tubes, deposited at specific locations on the Martian surface in a system designed to allow a future retrieval mission to collect them. Chayava Falls material is among the samples that have been collected. Whether it will be returned to Earth as part of the sample return mission depends on a program that has faced its own complications, funding challenges, technical difficulties, and timeline uncertainties that have pushed the projected return date further into the future. But the scientific community's commitment to the goal has not wavered. The samples will come back. The question is when. And while the world waits, scientists continue to analyze every possible measurement that Perseverance's onboard instruments can provide, extracting every bit of information that the available technology can access, building the most complete possible characterization of Chayava Falls in preparation for the day when Earth's laboratories can take over. In the meantime, the discovery has already changed something fundamental about how scientists think about Mars. Before Chayava Falls, the working hypothesis for most astrobiologists was that Mars probably had the conditions for life during its early, wet period, but that whether life actually arose and left detectable evidence was entirely unknown, and the default assumption was that the evidence, if it existed at all, would be subtle and ambiguous. After Chayava Falls, the assessment has shifted. The evidence is not subtle. It is not ambiguous in the sense of being difficult to see or characterize. What is ambiguous is its interpretation, but the data itself is clear, multi-layered, and internally consistent in ways that demand serious engagement. Mars, it turns out, may have been hiding something extraordinary in plain sight. The pattern was always there, waiting to be found. The instrument capable of finding it arrived in 2021. And in July of 2024, a drill cut through billions of years of silence and revealed it. The red planet has always invited our projections and fantasies. Since the early astronomers first studied its rust-colored surface through primitive telescopes, Mars has occupied a special place in the human imagination. It has been the home of invading armies in fiction, the destination of explorers in film, the focus of philosophical speculation about the nature of life and the extent of the universe's hospitality to living things. We have always wanted Mars to be inhabited, or at least to have been inhabited. That desire is not a weakness of reason. It is a recognition of the profound implications that another inhabited world would carry. But science has always demanded more than desire. It has demanded evidence. And for decades, the evidence was insufficient to the magnitude of the claim. Intriguing but not convincing. Suggestive but not compelling. Worth pursuing but not worth asserting. Chayava Falls may represent the first time that the evidence has begun to feel genuinely commensurate with the question being asked. Not proof not yet, perhaps not for years, but a real, substantive, multi-dimensional signal that points in a direction that cannot be ignored. A direction that, for the first time in the history of planetary science, makes the hypothesis of ancient Martian life feel less like a dream and more like a serious scientific position, supported by serious scientific data. The journey to this moment began long before Perseverance touched down on Mars in February of 2021. It began with a question that humans have asked since they first became capable of looking up at the night sky and wondering whether the lights they saw were surrounded by worlds like their own. It continued through centuries of telescopic observation, through the shock of realizing that Mars was not the lush, canal-crossed planet that some 19th century astronomers had imagined, through the sobering revelations of the early spacecraft missions, and through the slow, methodical accumulation of evidence that built, mission by mission, toward the moment when a drill on a robot billions of miles away found a pattern inside a rock that looked, to every expert who examined the data, like the chemical footprint of ancient life. This is the story of that journey, not just the discovery inside Chayava Falls, but everything that led to it. The geology of a planet that was once wet and warm and possibly alive, the biology of the organisms that, on Earth, leave exactly the signatures that Mars now appears to be showing us. The physics and chemistry of a world that lost its atmosphere, froze its water, and preserved its secrets in stone. The engineering and science behind the missions that have gradually, painstakingly, pulled those secrets toward the surface. And the question still unanswered, still electric with possibility of what it would mean for humanity to learn that we are not alone in the history of the solar system. That life, in some form, arose not just on Earth, but on its nearest planetary neighbor. That the chemistry of biology is not a single improbable miracle, but a recurring phenomenon, capable of emerging wherever conditions allow. That is the question that Chayava Falls has put squarely on the table. It is the most important question in the history of space exploration. And for the first time, we have something that might be an answer. To fully grasp the significance of what Perseverance found inside Chayava Falls, we need to step back from the immediate drama of the discovery and engage with the deeper scientific context that makes these findings so extraordinary. We need to understand Mars not as it is today, cold, dry, irradiated, and apparently dead, but as it was in its youth, when the conditions that made the discovery inside Chayava Falls possible were actively present. We need to trace the arc of a planet's life, from warm and wet to frozen and silent, and understand precisely why that arc matters for the question of biology. Mars formed approximately 4.5 billion years ago, in the same swirling disk of gas and dust that produced every other body in the solar system, including Earth. In those first hundreds of millions of years, the young planet was dramatically different from what we observe today. The surface was geologically active in ways that dwarf anything currently happening there. Enormous volcanoes erupted continuously, pouring vast quantities of gas into the atmosphere, water vapor, carbon dioxide, nitrogen, sulfur compounds building up a thick blanket of air around the young planet that was capable of trapping heat from the distant sun. The atmospheric pressure at the Martian surface during this period was likely comparable to Earth's, or possibly even higher. And with that thick atmosphere trapping heat, the surface temperatures could support something that seems almost impossible to imagine when looking at Mars today. Liquid water. Abundant, persistent, flowing liquid water. The evidence for this ancient water is preserved across the Martian surface in ways that decades of orbital and surface observation have made unambiguous. Valley networks carved into ancient highlands by running rivers, their branching patterns unmistakably similar to terrestrial river systems shaped by rainfall and surface runoff. Ancient lake basins, their shorelines still visible to trained eyes interpreting orbital imagery, their floors covered with sedimentary deposits laid down by water. Mineral deposits that form only in the presence of liquid water clays, sulfates, carbonates distributed across vast regions of the planet's surface. The water was there. The geological record is unambiguous on this point. Mars had water, and it had that water for long enough to carve channels, fill basins, and deposit thick sequences of sedimentary rock. The key question for astrobiology has always been not whether Mars had water, but whether it had water for long enough and under stable enough conditions for life to begin. Because the origin of life, even on Earth, is not instantaneous. The transition from chemistry to biology, from complex organic molecules reacting in water to self-replicating systems capable of Darwinian evolution, almost certainly required time. How much time is unknown, but estimates based on the earliest evidence of life on Earth suggest that biology may have appeared within a few 100 million years of conditions becoming favorable. That is a long time by human standards, but relatively brief in geological terms. The window of habitability on early Mars, the period during which liquid water was stable at the surface and conditions were favorable for the kind of chemistry that could produce life, is currently estimated to have lasted somewhere between several 100 million and possibly a billion years. This is a window that overlaps with the period during which life originated on Earth. If the origin of life is a process that occurs reliably, or even commonly, given appropriate conditions, then Mars had those conditions for long enough for it to happen. Jezero Crater sits within a region of Mars that is among the most ancient on the planet's surface. The highlands surrounding the crater preserve some of the oldest rocks on Mars, laid down during the period when the planet was at its most geologically active and its most hydrologically dynamic. The river that carved the delta inside Jezero, the river whose ancient channel is now called Neretva Vallis, flowed during this early wet period. The sediments it deposited in the ancient lake are contemporaneous with the window of maximum habitability. If life ever existed on Mars, the rocks of Jezero Crater are among the most likely places in the solar system to preserve evidence of it. This is not coincidence or lucky guessing. It is the result of years of careful geological analysis by scientists who studied every available image and every available measurement before the Perseverance mission was launched. The selection of Jezero as the landing site was a scientific decision of enormous consequence, made by people who understood exactly what they were looking for and why this particular place was the best available candidate for finding it. And now, with the discovery inside Chayava Falls, that careful reasoning appears to have paid off in ways that even the most optimistic members of the science team might not have expected. But to understand the full picture, to appreciate not just the excitement of the discovery, but also the complexity of the scientific and geological context in which it sits, we need to go further into the story of what happened to Mars after its wet period ended. Because the death of a planet is not instantaneous, and the processes that killed Mars's surface habitability are themselves part of the evidence that Perseverance is trying to decode. The story of Mars's transformation from a potentially living world to the frozen desert we observe today is fundamentally a story about magnetic fields and atmospheres and the relentless energy output of a star. Deep inside a planet, if the core is liquid and composed of electrically conductive material, the rotation of the planet combined with convective movement in the core can generate a powerful magnetic field. This is what happens inside Earth. The liquid outer core, composed primarily of iron and nickel, churns in complex patterns driven by the planet's rotation and the heat flowing outward from the inner core. This churning generates electric currents, and those currents generate a magnetic field that extends far into space around the planet. The field deflects the stream of charged particles that flows constantly outward from the sun, the solar wind pushing those particles around the planet, rather than allowing them to strike the atmosphere directly. Earth's magnetic field is the invisible shield that has protected our atmosphere for billions of years, preserving the conditions that allowed life to develop and persist. Mars, being smaller than Earth, had a similar but weaker magnetic field in its early history. The planet's interior was hot enough in its youth to maintain a liquid core and the convective processes that generate a geodynamo. Ancient Martian crustal rocks carry traces of this early magnetic field, magnetized in patterns that record the directions of the field as it existed when those rocks formed. The evidence is clear. Early Mars had a global magnetic field. It was not as strong as Earth's, but it was present. And while it was present, it provided some degree of protection for the young Martian atmosphere. But Mars's smaller size carried an inevitable consequence. Smaller planets cool more quickly than larger ones, because they have more surface area relative to their volume through which heat can escape. Earth, large enough to retain its internal heat across billions of years, still has an active geodynamo today. Mars, smaller and therefore cooling faster, eventually reached a state where the core solidified sufficiently to shut down the convective processes that generated the magnetic field. Based on the evidence preserved in ancient Martian rocks, this transition appears to have occurred approximately 4 billion years ago, roughly 500 million years after the planet formed. When the magnetic field died, Mars became vulnerable. Without the protective magnetosphere, the solar wind, a continuous stream of charged particles flowing outward from the sun at hundreds of kilometers per second, began to interact directly with the upper layers of the Martian atmosphere. The process is called atmospheric sputtering, and while it operates slowly by human timescales, it is relentless and cumulative. Energetic solar wind particles collide with atmospheric molecules, imparting enough momentum to kick those molecules into trajectories that carry them away from the planet entirely. Over millions and then billions of years, Mars's atmosphere was gradually stripped away, molecule by molecule, into interplanetary space. The transformation was devastating in its implications for the surface. As the atmosphere thinned, it lost its ability to trap heat, and temperatures fell. As temperatures fell, water that had been liquid at the surface began to freeze. As water froze and was removed from the atmospheric cycle, the greenhouse effect of water vapor declined, causing further cooling, causing more freezing, a feedback loop that accelerated the transition toward the cold, dry conditions that characterize Mars today. Water that was not frozen in polar ice caps or incorporated into minerals was gradually lost to space as well, as the tenuous atmosphere could no longer hold water vapor against the energy of the solar wind. The timescale of this transformation was not a sudden catastrophe, but an extended decline. For hundreds of millions of years after the magnetic field weakened, Mars retained enough atmosphere and enough liquid water to potentially maintain habitable conditions in some locations. Deep lakes, protected by surrounding terrain. Subsurface aquifers, insulated from the increasingly hostile surface. Hydrothermal systems, warmed by geological heat even as the surface grew colder and drier. Life, had it originated during the early wet period, might have persisted for far longer than a simple reading of the planetary timeline would suggest. The organisms that may have left their chemical signatures in the rocks of Jezero Crater did not necessarily live at the peak of Martian habitability. They may have been the inheritors of an already changing world, microbes that had adapted to increasingly harsh conditions over millions of years, retreating to the final refuges of liquid water as the planet dried and froze around them. Their remains, if the signals in Chayava Falls are indeed biological, are the last chapter of a biological story that began with the young planet's warmth and ended with the extinction of the last habitable environments. The average surface temperature on Mars today is approximately -80 degrees Fahrenheit. The atmospheric pressure is so low that liquid water cannot exist at the surface. It would either freeze instantly or boil away. The ultraviolet radiation that reaches the surface, unfiltered by any meaningful atmosphere, would destroy complex organic molecules in relatively short periods of time if they were exposed. The conditions that make Mars such an effective preserver of ancient rocks, the absence of plate tectonics, the minimal erosion by liquid water in the modern era, are the same conditions that make the planet look so inhospitable to present-day life. But they also make Mars an extraordinary repository of ancient information. On Earth, the geological record, older than about 3.5 billion years, has been largely erased by the very processes that make our planet so dynamic and hospitable to life today. Plate tectonics recycles old crust into the mantle and creates new rock from below. Liquid water erodes, dissolves, and chemically alters the exposed surface. Biological activity continuously overprints the chemical record left by earlier organisms. Earth is alive, and its aliveness obscures its ancient past. Mars is dead, and its deadness preserves it. The rocks of Jezero Crater have been sitting undisturbed for 3.5 billion years. The chemical signatures inside them, whatever their origin, have not been significantly altered by ongoing geological processes, because those processes essentially stopped operating long ago. What Perseverance is reading inside Chayava Falls is, to an extraordinary degree, a direct message from the ancient Martian environment. Not a heavily overprinted, repeatedly altered, partially destroyed record like the one we wrestle with on Earth when studying the origins of life, but something closer to a pristine archive. This is one of the most underappreciated aspects of Mars exploration. The planet's very hostility to present-day life is what makes it such an extraordinary place to search for evidence of past life. The cold, dry, geologically quiet surface of modern Mars is a perfect preservation environment. If biology left its marks in Martian rocks 3.5 billion years ago, those marks have had an extraordinary chance of surviving to the present day, essentially intact. The discovery of what may be exactly such marks inside Chayava Falls therefore carries an additional layer of significance. It is not just evidence that may point to ancient biology. It is evidence that has survived 3.5 billion years of preservation in one of the most stable geological environments in the solar system. Its survival is itself a kind of testimony to the robustness of biosignatures, to the fact that life, once it establishes a chemical foothold in rock, can leave a record that endures across timescales that challenge the human imagination. Understanding this context makes the careful work of the Perseverance science team all the more impressive. They are not just examining a rock. They are reading a document written in chemical language by processes that operated when the solar system was young, preserved through geological time by a planet's quietness, and now decoded by instruments capable of operating at the frontier of analytical sensitivity. The chain of causation that connects the ancient Martian environment to the laboratory results that landed on computer screens in Pasadena in the summer of 2024 is one of the most extraordinary in the history of science. And yet the story does not end with Chayava Falls. The discovery, significant as it is one data point, a remarkable, unprecedented, potentially world-changing data point, but a single sample from a single location. The scientific case for ancient life on Mars will ultimately be built not from a single compelling sample, but from a body of evidence accumulated across multiple samples, multiple locations, and multiple lines of analysis. Perseverance has collected dozens of samples during its mission, and the analysis of those samples, particularly once they are returned to Earth, will either reinforce and expand the picture that Chayava Falls began to paint, or complicate it in ways that require reinterpretation. This is how science works. Individual discoveries, however spectacular, are starting points rather than endpoints. The discovery of potential biosignatures in a single Martian rock is the beginning of a scientific investigation, not its conclusion. It changes the questions that researchers are asking. It focuses attention on specific aspects of the geological and chemical record. It motivates more detailed analysis, more precise measurements, more creative experimental approaches to test the biological hypothesis. And it will continue to do so until the scientific community reaches a consensus, which may take years, possibly decades, about what Chayava Falls actually tells us about the history of life in the solar system. In the meantime, the broader exploration of Mars continues on multiple fronts, each adding pieces to a puzzle whose dimensions and significance are only now becoming fully apparent. The Curiosity rover, which has been exploring Jezero Crater, a very different geological environment from Jezero since 2012, has its own contributions to make to the accumulating picture of Martian habitability and potential biology. Curiosity has confirmed the presence of organic molecules in Martian rocks and sediments at multiple locations within Jezero Crater. These organics have survived for billions of years in a geological context that would have been habitable during the early period of Mars's history. The specific organic molecules detected by Curiosity include compounds like thiophanes, benzene, and propane carbon-based molecules that, on Earth, can be produced by both biological and non-biological processes, but whose presence in ancient sedimentary rock is consistent with what would be expected if organic carbon had been processed through biological activity. Curiosity has also detected seasonal variations in the concentration of methane in the Martian atmosphere. Methane is a molecule of particular interest for astrobiology because, in an oxidizing environment like the Martian atmosphere, it breaks down relatively quickly on timescales of centuries to millennia. The fact that methane is detectable at all in the Martian atmosphere means it is being replenished from somewhere. On Earth, the dominant source of atmospheric methane is the metabolic activity of microorganisms. Non-biological sources of methane exist as well, including geological processes involving water and rock chemistry. The seasonal variations in Martian methane concentration hint at a source that is sensitive to temperature changes, which could be consistent with either biological activity in the subsurface or with geological processes that operate more vigorously during warmer periods. The methane signal from Curiosity has been controversial. Some measurements have detected it clearly, while others from orbital instruments have failed to confirm it, leading to scientific debate about whether the signal is real or an artifact of measurement. But the possibility that methane in the Martian atmosphere could indicate ongoing biological activity even today not just in the ancient past, is taken seriously enough that it has motivated dedicated scientific inquiry. If Mars currently hosts microbial life in the subsurface, shielded from radiation by meters of rock, metabolizing carbon compounds and occasionally releasing methane that diffuses upward and escapes into the atmosphere, the methane signal would look exactly like what Curiosity has detected. This possibility present-day life on Mars, not just ancient life, is one that most scientists approach with great caution, but do not dismiss. The deep subsurface of Mars, where liquid water may still exist in certain geological contexts and where radiation from space cannot penetrate, remains largely unexplored. The surface missions that have operated so far are confined to the upper meter or so of the Martian soil and rock, scratching at the surface of a planet whose interior is almost entirely unknown. What exists below the permafrost layer? What chemistry operates in deep fractures filled with briny water? What biology might persist in environments completely cut off from the surface? These are questions that current missions cannot answer. The planned ExoMars rover mission, developed by the European Space Agency with contributions from international partners, is designed to address the subsurface question. Carrying a drill capable of reaching 2 meters below the Martian surface, the mission aims to access rock and soil that has been shielded from surface radiation and has not been exposed to the harsh oxidizing chemistry of the Martian atmosphere. At those depths, if life ever retreated underground as the surface became increasingly hostile, its chemical signatures might be far better preserved than anything accessible to surface missions. The biological potential of the Martian subsurface is something that Mars science will be grappling with for generations. But the most transformative moment in the search for life on Mars, the moment that will either confirm or conclusively refute the biological hypothesis raised by Chayava Falls, will come when Martian samples arrive on Earth. The analytical tools available in terrestrial laboratories are orders of magnitude more sensitive and diverse than anything that can be flown on a spacecraft. Measurements that take minutes in an Earth laboratory would require years of rover operations. Experiments that would require kilograms of material can be done in a terrestrial lab with milligrams. And crucially, the samples can be subjected to experiments that were not conceived of when the mission was designed, experiments that will be developed by scientists working in response to the specific questions raised by what Perseverance has already found. The Mars Sample Return Program represents one of the most complex and ambitious engineering challenges in the history of space exploration. The plan involves a future lander mission that will deploy a small rocket from the Martian surface, launching the cached sample tubes into Mars orbit. An orbiting spacecraft will then rendezvous with the sample container, capture it, and carry it back to Earth. The samples will arrive in a sealed container designed to prevent any possible contamination of Earth's environment by Martian material, and they will be delivered to a dedicated sample curation facility where they will be studied under conditions of extraordinary cleanliness and precision. The scientific community has been waiting for these samples with a patience born of understanding what is at stake. Return samples from Mars will not just address the question of ancient life. They will provide unparalleled insight into the early history of the inner solar system, the processes that shaped Mars's geological evolution, the behavior of water chemistry in ancient lake environments, and the fundamental question of how likely life's origin is when appropriate conditions are present. They will be among the most scientifically valuable objects ever brought to Earth, studied by researchers across disciplines for generations. And within that collection of returned samples, the material from Chayava Falls occupies a special position. It is the sample that has already produced the most compelling potential biosignatures. It is the sample that the broader scientific community has been watching most closely since the discovery was announced. When it arrives in a terrestrial laboratory, and the scientific and political will to make that happen has only intensified since the July 2024 discovery, the instruments will be the most powerful in human analytical science, and the questions they will be asked to answer will be the most important in the history of the search for life beyond Earth. What kinds of analyses will those laboratories perform? The range is extraordinary. Isotopic measurements of carbon, nitrogen, and sulfur in the organic molecules can distinguish between biological, and non-biological sources with much higher precision than is possible with Perseverance's instruments. On Earth, biological processes preferentially incorporate certain isotopes over others in ways that produce characteristic ratios that serve as a reliable biosignature in ancient terrestrial rocks, and that should, if the biology is universal in its basic chemistry, apply to Martian organisms as well. Electron microscopy can reveal structures at the nanometer scale sizes, at which individual bacterial cells and their remnants become visible. If microbial fossils are present in the Chayava Falls material, electron microscopy will find them. The technique has been used to study the controversial ALH 84001 Mars meteorite samples that generated such excitement in 1996, and it has been refined significantly since then. Modern electron microscopy can distinguish between microbial structures and non-biological mineral formations with much greater reliability than was possible 30 years ago. Secondary ion mass spectrometry, a technique that can identify the chemical composition of specific microscopic features within a rock sample with extraordinary precision, will be brought to bear on the spatial relationships between the organic molecules, the iron minerals, and the phosphate deposits that PIXL detected in Chayava Falls. The ability to determine, at the scale of individual micron-sized grains, exactly what compounds are present and how they are associated with each other will dramatically constrain the range of interpretations available for the data. And perhaps most importantly, the samples will be available for experiments that have not yet been conceived. The history of science is full of cases where the most important discovery came not from the experiment that was planned, but from the experiment that was inspired by an unexpected observation. When researchers around the world have access to actual Martian material, not measurements made by robotic instruments, but physical samples they can hold, section, dissolve, vaporize, and interrogate with every technique at their disposal, the rate of discovery will accelerate in ways that are difficult to predict. This is the scientific future that the discovery inside Chayava Falls is pointing toward. A future in which the question of life on Mars is not a matter of speculation or hopeful interpretation of ambiguous data, but a scientific question that humanity is actively and concretely working to answer, with the tools and the samples needed to reach a definitive conclusion. The emotional weight of this trajectory is difficult to overstate. We are, for the first time in human history, in a position where the answer to the question of whether life exists beyond Earth is not infinitely deferred, not a matter of future technology or future missions or future understanding that lies beyond the horizon of current possibility. We have samples. We have a destination Earth for those samples. We have laboratories ready to receive them. We have a generation of scientists trained specifically to answer these questions, equipped with techniques developed for exactly this purpose. The answer is not here yet, but it is closer than it has ever been. It is within reach in a way that would have seemed almost incomprehensible to the scientists who first began seriously asking the question of whether Mars might harbor life. And the evidence from Chayava Falls, that array of dark spots, those concentrations of organic molecules, those deposits of iron minerals and phosphates at the boundaries where chemistry was most active, sits at the center of that trajectory. It is the most specific, most detailed, most chemically coherent signal that Mars has yet transmitted to us about its biological past. Whatever the final interpretation of that signal turns out to be, it has fundamentally changed the terms of the conversation. Before July 2024, the scientific mainstream could describe the question of ancient life on Mars as open and interesting, but without strong positive evidence. After July 2024, the scientific mainstream must contend with a specific, detailed, multi-instrument dataset that points positively in the direction of biology. The burden of proof has shifted, subtly but unmistakably. The null hypothesis that Mars was always lifeless now requires explanation of why the features inside Chayava Falls look so biological, why they occur at this location, in this geological context, with this specific combination of chemical signatures. It requires a non-biological mechanism capable of producing all of these features simultaneously. And while such mechanisms are possible in principle, they are not immediately obvious, and the scientific community is actively working to either identify them or rule them out. This is the scientific process working exactly as it should. Extraordinary claims require extraordinary evidence. The evidence from Chayava Falls, while not yet sufficient to establish certainty, is already extraordinary enough to demand serious engagement. It has moved the question of Martian life from the periphery of scientific discourse to its center. It has mobilized resources, focused attention, and accelerated the timeline of analysis in ways that will have lasting consequences for how we understand the universe. Mars has always been the most human of the other planets. Its color, visible to the naked eye, has given it a place in mythology and imagination across every human culture. Its proximity and its seasonal visibility have made it the neighbor that humanity has watched most closely, wondered about most deeply, and explored most extensively. And now, it may be on the verge of delivering the most significant answer to the most significant question that our species has ever asked. Are we alone? The rocks of Jezero Crater may already contain the answer. The instruments aboard Perseverance may already have detected it, in the form of dark spots against a pale background, in the distribution of organic molecules, in the chemical map produced by X-ray fluorescence of an ancient Martian stone. The answer may already exist, encoded in samples sitting in titanium tubes on the surface of another world, waiting to make the journey home. What we know, with certainty, is that we are closer to the answer than we have ever been. And that closeness, that sense that the boundary between not knowing and knowing is no longer impossibly distant, is itself a transformation in how humanity relates to the universe. We are not the final answer to the question of cosmic life. We are, at most, one expression of a phenomenon that may be far more widespread than we have ever allowed ourselves to believe. The evidence from Chayava Falls does not prove this, but it makes it, for the first time, scientifically reasonable to consider it as something other than speculation. And that shift from speculation to scientific possibility supported by concrete evidence is itself one of the most significant developments in the history of human thought about our place in the cosmos. To fully appreciate where this story might lead, we need to look at the broader scientific and philosophical implications of what a confirmed discovery of ancient life on Mars would mean not just for planetary science, but for biology, for our understanding of the origin of life, for the search for life beyond the solar system, and for the question of humanity's long-term relationship with the universe we inhabit. Begin with biology. The origin of life on Earth is one of the deepest unsolved problems in all of science. We know that life exists. We know, in broad outline, what chemistry life uses. We know, from the geological record, approximately when life appeared on Earth within the first billion years of the planet's history, possibly within the first few 100 million years. What we do not know is how. The transition from complex chemistry to self-replicating biology is a process that has never been observed in action and has never been successfully recreated in a laboratory. The specific sequence of chemical steps that led to the first organism capable of Darwinian evolution remains unknown. This ignorance is profound and humbling. It means that we do not know, in a fundamental sense, how we came to exist. The discovery of evidence of life on Mars would provide a constraint on this problem of enormous value. If life arose independently on Mars, not transported from Earth, or from Mars to Earth, but originating separately under similar conditions, it would tell us something crucial about the origin of life. That it is not a single, vanishingly improbable accident confined to the specific circumstances of early Earth, but a process that can occur reliably, or at least repeatedly, in environments that meet certain basic criteria. This would be evidence that the origin of life is governed by chemistry that, given the right conditions, tends toward biology. That life is, in some meaningful sense, a natural outcome of planetary chemistry under the right circumstances. This has profound implications, not just for understanding our own origins, but for the search for life beyond the solar system. Thousands of exoplanets have been discovered in recent years. many of them in the habitable zones of their parent stars where liquid water could exist on the surface. The question of how many of those planets might host life is currently unanswerable because we have only one data point, Earth. With a single example of life-bearing planets, we cannot determine whether life is common or rare. With two, Earth and Mars, we begin to have a sample size that allows statistical inference. If two neighboring planets in the same solar system both developed life during a period when both had liquid water, the implication is that life originates readily wherever conditions allow, and that the universe is likely teeming with inhabited worlds. This is not a conclusion that would be immediately and universally accepted. The scientific debate about the interpretation of two data points would be extensive and nuanced. But the direction of the reasoning is clear, and its implications are profound. Finding life on Mars would not just tell us about Mars, it would tell us about the cosmos. The question of whether Martian life, if it existed, was related to Earth life is one that scientists take seriously and that the detailed analysis of returned samples would be positioned to address. Mars and Earth have been exchanging material throughout their histories. Large impacts on either planet can eject surface rocks into space with sufficient velocity to escape planetary gravity, and some fraction of these rocks eventually land on the other planet. We know this happens. We have identified Martian meteorites on Earth, rocks that originated on Mars and were transported to our planet by exactly this mechanism. The process of lithopanspermia, as it is called, raises the possibility that life could be transported between planets inside rocks, surviving the journey through space and the impact of landing. If Martian life and Earth life are related, if one world was seeded by the other during the early period, when both were habitable, the chemical analysis of Martian biosignatures should reveal a specific pattern. Earthly life uses a specific set of amino acids, the left-handed versions, out of the two mirror image forms that chemistry can produce equally. If Martian life used the same biochemistry, inherited from or related to Earth life, it would show the same asymmetry. If Martian life originated independently, it might show a different biochemical signature, perhaps the right-handed amino acids, perhaps a completely different set of biochemical building blocks that evolution found equally effective under Martian conditions, but that took a different path than the chemistry of terrestrial biology. This distinction-related life versus independent life is one of the most important questions that returned sample analysis could address, and the answer would have enormous implications. Independent origin of life on Mars would be far more significant for our understanding of the universe than a demonstration that Mars was seeded from Earth, or vice versa. It would mean that life found two separate paths to the same destination, starting from different initial conditions in the same solar system. That would be the strongest possible evidence that life is a robust, recurring phenomenon rather than a singular accident. The implications extend outward from biology into philosophy, and even into questions about humanity's long-term future. If Mars once harbored life, if the solar system is, or was, a place where biology emerged on multiple worlds, then the question of human colonization of Mars takes on new dimensions. The planetary protection protocols that govern space missions, the rules designed to prevent contamination of other worlds by Earth life, and vice versa, would need to be reconsidered in light of evidence that Mars already has its own biological history. The ethical questions around human presence on a world that may have been, or may still be, biologically active are not simple, and they will require serious engagement from science, philosophy, and policy as the evidence accumulates. The broader question of humanity's relationship to the universe is also transformed. We are a species that has, throughout our history, grappled with questions of uniqueness and significance. The realization that Earth is not the center of the solar system, that the Sun is not the center of the galaxy, that the galaxy is one of hundreds of billions. Each of these realizations expanded our sense of scale and challenged our sense of special status. The discovery of life on Mars would be another such expansion, not a diminishment of life's significance, but a revelation that life's significance is even greater than we had thought. Life is not a fragile, improbable accident confined to a single planet in an otherwise sterile universe. It is something that the universe makes, given the right conditions, in multiple places across billions of years of chemical and geological evolution. This is a vision of the cosmos that is simultaneously humbling and inspiring. Humbling because it displaces us from a position of unique cosmic importance. Inspiring because it places us within a universe that is alive in ways we are only beginning to understand, a participant in a phenomenon of cosmic scope rather than a lonely anomaly in an otherwise empty darkness. The rocks of Jezero Crater are whispering this story. The instruments of perseverance have begun to hear it. The scientists who analyze the data are carefully, rigorously, responsibly working to understand what is being said. And the world, the broader human community that will ultimately receive whatever conclusion the scientific process delivers, is waiting, with a mixture of anticipation and appropriate skepticism, to learn whether what we are hearing is indeed the voice of ancient life, speaking from across 3.5 billion years of silence. The story is not yet complete. The most important chapter, the definitive analysis of returned samples, has not yet been written. But the narrative arc is visible, and it is pointing in a direction that would have seemed almost impossibly optimistic to the scientists of a generation ago. We are on the verge of knowing. We are closer to an answer than we have ever been. And the evidence that has brought us to this threshold, the dark spots against a pale background inside a Martian rock called Chayava Falls, may prove to be one of the most consequential scientific observations in the history of human inquiry. Mars has always known something we did not. For billions of years, it has held its secrets sealed inside stone, frozen under dust, waiting at a distance of hundreds of millions of miles for a civilization capable of sending the right instrument to ask the right question. We may finally have done both. And the answer, when it comes, whether it confirms biology or forces us to find a different explanation for everything Chayava Falls has shown us, will change how we see ourselves, how we see our planet, and how we see the universe we are only just beginning to explore. The question that Chayava Falls has placed before humanity is not one that arrived without precedent. It did not emerge fully formed from a single drilling operation on a single July morning. It grew slowly, over decades, through the accumulated effort of thousands of scientists and engineers who devoted their professional lives to understanding a planet that offered answers reluctantly, that revealed its secrets in fragments, that demanded extraordinary patience and extraordinary ingenuity before yielding anything approaching clarity. To fully appreciate where we stand today, we need to understand the long road that brought us here, the missions, the discoveries, the setbacks, and the gradual accumulation of understanding that made the findings inside Chayava Falls both possible and comprehensible. The modern era of Mars exploration began with the Mariner missions of the 1960s. These early spacecraft, primitive by contemporary standards, flying past Mars on brief trajectories that allowed only minutes of close observation, returned the first detailed images of the Martian surface. What they showed was deeply discouraging to the scientific community of the time. Mars appeared to be heavily cratered, ancient, and utterly inert. The surface looked more like the moon than like anything that had ever been imagined as a possible home for life. The early hopes inspired by 19th century telescopic observations, the idea that Mars might have vegetation, might have canals, might harbor some form of intelligent or at least biological life, collapsed under the weight of these images. Mars, the early data suggested, was dead. But the Mariner missions covered only small fractions of the total Martian surface. And when the Mariner 9 spacecraft entered orbit around Mars in 1971 and began the first systematic global mapping of the planet, the picture changed dramatically. Mariner 9 discovered enormous volcanoes larger than anything on Earth. It found Valles Marineris, a canyon system that stretches across a quarter of the planet's circumference and descends to depths that dwarf the Grand Canyon by every measure. And it found something that the earlier flyby missions had entirely missed: ancient river valleys carved into the highland terrain with the unmistakable branching geometry of drainage networks formed by flowing water. The discovery of ancient river valleys on Mars was a turning point. It did not prove that Mars had been habitable, but it demonstrated conclusively that the Mars of the present was not the Mars that had always existed. The planet had changed. And the direction of that change from a world with flowing water to the cold, dry desert of today implied a past that had been dramatically different from what the early Mariner images had suggested. The Viking program of the mid-1970s represented humanity's first serious attempt to search directly for life on Mars. 2 landers touched down on the Martian surface in 1976, each carrying a biology package designed to detect the presence of living organisms in the Martian soil. The experiments were clever and carefully designed. They exposed Martian soil to nutrients and measured whether any gases were produced, looked for uptake of radioactively labeled carbon compounds, and performed chemical analyses of the soil itself. The results were deeply ambiguous. Some of the experiments produced signals that, if detected in a terrestrial soil sample, would have been interpreted as evidence of biological activity. But the chemical analysis instrument found no organic molecules in the Martian soil, a result that seemed incompatible with the presence of life, since all known life produces organic compounds. The scientific community spent years, decades, debating the Viking results. The consensus that eventually emerged was that the reactive signals detected by the biology experiments were most likely the result of chemical oxidants in the Martian soil that could mimic biological reactions without any biological involvement. The absence of organic molecules was taken as the more decisive result, suggesting that the Martian soil was sterile. Mars, the mainstream concluded, was probably lifeless. But that conclusion rested on an assumption that later missions would undermine. The Viking landers had searched for organic molecules using an instrument that, it was subsequently realized, might not have been sensitive enough to detect organics at the concentrations present in the Martian soil, particularly if those organics were combined with the reactive perchlorates that later missions would discover to be widespread on Mars. When organic compounds mixed with perchlorates are heated, which is how the Viking instrument prepared its samples for analysis, the reaction can destroy the organics before they can be detected, producing instead simple combustion products that the instrument might not have been looking for. The absence of organics in the Viking data may have been an artifact of the analytical method rather than a genuine reflection of the Martian chemistry. This realization, which came to full clarity only decades after the Viking missions, illustrates one of the fundamental challenges of Mars exploration. The planet's chemistry is not Earth's chemistry. Instruments designed with Earth's environment as their reference framework may systematically misread Martian data. The lesson was expensive to learn. It took 30 years and multiple missions to fully appreciate, but it ultimately drove the development of the more sophisticated analytical approaches that Perseverance carries today. The Mars Pathfinder mission of 1997 and the Mars Global Surveyor orbital mission that ran from 1997 to 2006 continued the accumulation of knowledge. Pathfinder's small rover, Sojourner, demonstrated that rovers were viable tools for Martian exploration, paving the way for the larger and more capable rovers that followed. Global Surveyor's cameras and instruments mapped the Martian surface and atmosphere in unprecedented detail, confirming and extending the picture of a planet with a complex geological history involving abundant ancient water. The Spirit and Opportunity rovers, which landed in January 2004, represented a quantum leap in capability. Spirit, which operated for more than 6 years before becoming permanently immobile in soft soil, explored Jezero Crater and discovered evidence of ancient hydrothermal activity, hot water interacting with rock in the Columbia Hills region. Opportunity, which operated for nearly 15 years before being silenced by a global dust storm in 2018, explored the Meridiani Planum region and made one of the most definitive early demonstrations of ancient water on Mars. The small gray spherical formations that Opportunity found scattered across the surface, nicknamed blueberries by the science team, were identified as concretions of hematite. an iron mineral that forms in the presence of water. And the layered sedimentary rock outcrops that Opportunity studied showed clear evidence of having been deposited by water that flowed and ponded in the ancient past. Opportunity's discoveries at Meridiani Planum established beyond reasonable doubt that water had existed on Mars in the past, that it had been present for extended periods, and that the chemistry of the water, somewhat acidic, mineral-rich, was consistent with what had been present in the early solar system. The question was no longer whether Mars had had water. The question was whether that water had persisted long enough and under conditions hospitable enough for life to develop. The Curiosity rover, which landed in Gale Crater in August 2012, was designed specifically to address the habitability question. Its instrument suite was the most sophisticated ever sent to Mars, and its findings rapidly confirmed what the science team had hoped. Gale Crater had once hosted a lake. The ancient lake in Gale Crater had been filled with fresh water, not the acidic, highly saline water that Opportunity had found evidence of at Meridiani, but water with a neutral pH and a chemical composition remarkably similar to the kind of fresh water that supports life on Earth. The lake sediments in Gale Crater contained all the chemical ingredients that life, as we know it, requires: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, all in forms that organisms could use. Curiosity's findings at Gale Crater were transformative. They shifted the scientific consensus from Mars may have been habitable to Mars was definitely habitable, at least for a period of millions to perhaps hundreds of millions of years. This was an enormous step. Habitability is not life, but it is the prerequisite for life. And the confirmation that Mars had genuinely habitable environments in its past placed the question of whether life actually arose in those environments on a completely different scientific footing. Curiosity also detected organic molecules in Gale Crater sediments, complex carbon compounds preserved in ancient rock, surviving despite the harsh radiation environment. The detection of these organics was significant because it demonstrated that Mars could preserve organic chemical information across billions of years, giving hope that the more specific biosignatures that Perseverance might find at Jezero Crater would also have survived if they were ever deposited. When Perseverance landed in Jezero Crater on the 18th of February 2021, it did so in a landing sequence of terrifying precision and complexity. The spacecraft entered the thin Martian atmosphere at hypersonic velocity, using an aeroshell to slow its descent before deploying a parachute, then firing retro-rockets to slow further, and finally using a remarkable sky crane mechanism, a hovering rocket, powered descent stage that lowered the rover on cables to the surface before flying away and crash landing at a safe distance. The entire sequence, which engineers called the 7 minutes of terror, because it took that long for events to unfold, while the communication delay meant that mission control on Earth could receive no live information and could make no adjustments, worked flawlessly. Perseverance touched down in the precise region of Jezero Crater that the science team had selected, close to the ancient delta deposits that were the primary scientific target. In the months and years that followed, Perseverance systematically explored its landing site, drilling into rocks, collecting samples, and transmitting data back to Earth. It confirmed that Jezero Crater had indeed been a lake. It found layered sedimentary deposits consistent with material that had been transported by the ancient river and deposited as the river entered the lake and slowed. It detected organic molecules in multiple locations. And then, in July 2024, it drilled into Chayava Falls and found the leopard spots. The rover also carried a small experimental helicopter, Ingenuity, which became the first powered aircraft to fly on another planet. Ingenuity was originally designed as a technology demonstration, intended to make just a few short flights to prove that powered flight was possible in the thin Martian atmosphere. It performed so far beyond expectations that its operational role was extended again and again, ultimately serving as a reconnaissance aircraft for Perseverance. scouting routes, and identifying geological features of interest from an aerial perspective. The data that Ingenuity gathered helped the science team plan the rover's path through Bright Angel and toward the location where Chayava Falls was ultimately found. The accumulation of capability across these successive missions, from the first blurry Mariner images to the centimeter-scale precision of Perseverance's PIXL instrument, represents one of the great, sustained, technological achievements in human history. Each mission built on the knowledge gained by its predecessors. Each technological advance made the next set of questions answerable. The entire enterprise, spanning more than 6 decades and involving tens of thousands of scientists, engineers, and support personnel across multiple countries, has been directed toward a single fundamental question: are we alone? That question extends far beyond Mars. Even as Perseverance drills into Martian rocks and SHERLOC maps the distribution of organic molecules, missions elsewhere in the solar system are probing other environments where life might exist. The story of the search for life is not confined to the red planet. It extends outward to the gas giant moons that have become, in recent decades, some of the most exciting targets in astrobiology. Europa, one of Jupiter's 4 large moons, orbits within the intense radiation environment of the largest planet in the solar system. Beneath its icy surface, a shell of water ice that covers the moon's entire globe to a depth of tens of kilometers, a global subsurface ocean is maintained in liquid form by tidal heating. The gravitational tug-of-war between Jupiter and the other large moons flexes Europa's interior, generating heat that keeps the subsurface ocean from freezing, despite the moon's enormous distance from the sun. The ocean beneath Europa's ice may be as deep as 100 kilometers more liquid water by volume than exists on the entire surface of Earth. Europa's ocean is in contact with the rocky seafloor below it. On Earth, the interface between liquid water and warm rock, particularly at hydrothermal vents, is one of the most productive biological environments known. Hydrothermal vent communities on Earth support rich ecosystems of organisms that derive their energy entirely from chemical reactions involving the fluids emerging from the vents, with no dependence on sunlight whatsoever. These communities have demonstrated that life on Earth is not confined to surface environments, not dependent on photosynthesis, and not limited to the relatively mild conditions of the shallow ocean. They have dramatically expanded our understanding of the range of environments in which biology can operate. The possibility that Europa's subsurface ocean hosts similar hydrothermal environments, and therefore similar biological communities, is taken seriously by the astrobiological community. NASA's Europa Clipper mission, launched in October 2024, is designed to conduct detailed reconnaissance of Europa, flying past the moon dozens of times and using a sophisticated instrument suite to characterize the ice shell, the ocean beneath it, and the moon's potential habitability. If the data returned by Europa Clipper supports the case for habitability, it will strengthen the argument for a future mission that could land on Europa's surface, drill through the ice, and directly sample the ocean below. Enceladus, a small moon of Saturn, provides an even more direct window into its subsurface ocean. Active geysers near the moon's south pole continuously eject water, ice particles, and organic compounds from the subsurface ocean into space, forming a plume that extends far above the moon's surface. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew directly through this plume and sampled its contents. The findings were remarkable. The plume material contains water, salts, silica particles that form only at specific high temperatures, consistent with hydrothermal activity. Molecular hydrogen, a chemical energy source that Earth organisms use to power metabolism, and complex organic molecules, including compounds that, on Earth, are associated with biological chemistry. Enceladus's plume material is, in effect, samples from a subsurface ocean being delivered to space for free. Future missions could fly through the plume and collect these samples without the engineering challenge of landing and drilling through ice. The Enceladus case for habitability is in some respects even stronger than Europa's. The moon is actively showing us its ocean chemistry in real time, and what we are seeing is consistent with an environment capable of supporting life. Titan, Saturn's largest moon, presents yet another kind of potential habitability. Unlike Europa and Enceladus, where the relevant chemistry involves liquid water, Titan's surface is covered by lakes and rivers and seas of liquid hydrocarbons, primarily methane and ethane, at temperatures so cold that conventional water-based life as we know it could not survive. But theoretical considerations suggest that alternative biochemistries, using liquid methane as a solvent instead of liquid water, might be possible. If such exotic life exists on Titan, it would be so different from anything known on Earth that detecting it would require entirely new frameworks for recognizing biology. The Dragonfly mission, a rotorcraft lander designed to fly between multiple landing sites on Titan's surface, is currently scheduled for launch in the late 2020s. It will study Titan's chemistry in detail, looking for patterns that might indicate biological activity, while also characterizing the moon's prebiotic chemical environment. Even if Dragonfly finds no life, it will advance our understanding of the range of environments where chemistry can organize itself into complex structures, and that understanding is directly relevant to the fundamental question of how life begins. The solar system, it turns out, is far more interesting from an astrobiological perspective than anyone imagined before the space age. Europa, Enceladus, Titan, and Mars are not the only candidates. Recent studies have suggested that even Venus, long dismissed as a hellish, entirely inhospitable world, might host microbial life in its upper cloud layers. Where temperatures and pressures are more moderate and complex chemistry has been detected. The cloud layers of Venus represent an environment that no mission has yet adequately explored, and the possibility that they harbor life, however exotic, cannot be dismissed on current evidence. The breadth of potential habitable environments within the solar system has fundamentally changed the landscape of astrobiology. The question is no longer whether any other world in the solar system might be habitable. The answer to that question is almost certainly yes, in the broadest sense of the term. The question is which of these worlds actually harbors life, and the answer to that question is what a generation of missions, led by the ongoing exploration of Mars, is actively working to determine. And yet Mars retains a special place in this search, for reasons that go beyond its relative accessibility. Mars is the world most like Earth that we know of in the solar system. It is the world that most clearly shows us what happens to a planet that starts out similar to our own, but follows a different evolutionary path. It is the world where the questions about habitability and biology are most directly tractable with current technology. And it is the world whose answer, whatever that answer turns out to be, will have the most direct implications for understanding our own planet's history and our species' future. The future of Mars exploration extends far beyond robotic missions. The plans for human missions to Mars, long discussed in theoretical terms, are becoming progressively more concrete, as the technical challenges of deep space human spaceflight are addressed by both government space agencies, private commercial entities. The Artemis program, which is returning humans to the moon for the first time since 1972, is explicitly designed in part as a proving ground for the technologies and operational approaches that will be needed for human Mars missions. Long-duration life support systems, radiation shielding for deep space travel, surface operations protocols, and in-situ resource utilization, the ability to extract water, oxygen, and other materials from the resources available at a destination, are all being developed and tested in the context of lunar exploration with Mars in mind. The timeline for human Mars missions remains uncertain. Technical challenges are formidable, costs are enormous, and the political and institutional will required to sustain a program of this complexity across multiple decades is difficult to guarantee. But the trajectory is clear, and the discovery at Chayava Falls may prove to be one of the most powerful motivators for maintaining that trajectory. Nothing galvanizes public and political support for space exploration like the possibility of life. And the possibility, for the first time supported by concrete multi-instrument evidence, rather than theoretical argument alone, that Mars once harbored living organisms is exactly the kind of discovery that reminds humanity why we explore. When humans eventually stand on the surface of Mars and the scientific and engineering communities working toward that goal believe it will happen within the next few decades. The experience will be shaped in ways large and scientific and fine debbies. Small by everything that has been learned through robotic exploration. The landing site will be chosen based on orbital and surface data accumulated over decades. The geological context that the first human explorers encounter will be understood at a level that would be impossible without the systematic reconnaissance that missions like Perseverance have provided. And the questions that those explorers will be trying to answer, perhaps most urgently, the question of whether Mars ever harbored life, will be questions that the robotic missions have already begun to frame. Human explorers on Mars will be able to do things that robotic missions cannot. They will be able to make real-time decisions about where to look and what to sample, responding to the geological context in ways that even the most sophisticated robotic systems cannot replicate. They will be able to conduct experiments requiring dexterity and judgment that lie beyond the capabilities of mechanical arms and automated instruments. They will be able to access regions that rover missions cannot reach: cliff faces, cave entrances, the walls of deep craters where ancient geological layers are exposed in cross-section. And they will be able to return samples in quantities and varieties that a robotic sample return mission, however cleverly designed, cannot match. The first human geologist to examine a rock face on Mars and recognize a potential biosignature with trained eyes will be participating in a moment of scientific and historical significance that is difficult to overstate. That geologist will be the culmination of everything that has led to that point. Every Mariner image, every Viking experiment, every meter driven by spirit and opportunity and curiosity and perseverance, every image processed, every spectrum analyzed, every paper written, every argument made, every funding battle won. The entire arc of Mars exploration leads to that moment of human recognition on the surface of another world. And the discovery inside Chayava Falls, the dark spots that launched the most serious biological investigation in the history of planetary science, may prove to be the landmark that defines where that arc turned decisively toward its destination. The moment when the abstract possibility of Martian life became a concrete scientific question with concrete evidence attached to it. The moment when the search for life on Mars stopped being entirely speculative and started being, at least partially, empirical. This transformation from speculation to evidence-based inquiry is the most significant thing about the Chayava Falls discovery, perhaps even more significant than the discovery itself. Science advances not just through individual findings, but through the transformation of questions. Questions that were previously unanswerable, in the sense that no available data bore on them, become answerable when evidence arrives that constrains the range of possible interpretations. The history of science is full of such transformations moments when a question that had seemed permanently open suddenly acquired enough empirical traction to be addressed through the normal processes of hypothesis testing and experimental confirmation. The biology of Mars has, for most of the history of Mars exploration, been an open question in the deepest sense, a question to which no available evidence spoke directly or compellingly. The Viking results were ambiguous and remain contested. The meteorite, ALH 84001, raised hopes that were not fulfilled. The organic detections by Curiosity were significant, but non-specific. None of these findings was sufficient to move the biological question from the realm of speculation to the realm of testable science. Chayava Falls may have changed that. The specificity of the biosignatures, the spatial correlation between organic concentration and mineral indicators of biological chemistry, the geological context of an ancient lake delta, the consistency of the pattern with what is known from Earth's oldest biological records provides the kind of multidimensional constraint that makes the biological hypothesis not just plausible, but scientifically addressable. There are now specific predictions that follow from the biological interpretation, predictions that can be tested with the instruments of terrestrial laboratories when the samples are returned. If the biological interpretation is correct, certain isotopic ratios should fall within specific ranges. Certain molecular structures should be present. Certain spatial relationships between compounds should hold at scales finer than Perseverance's instruments can resolve. These are testable predictions, and when the samples arrive on Earth, those tests will be run. Whatever they find will advance our understanding, either confirming the biological hypothesis with a level of rigor that the scientific community cannot dismiss, or falsifying it in ways that constrain what other explanations remain viable. Either outcome is scientifically valuable. Either outcome represents progress. This is what makes the current moment in Mars science so genuinely extraordinary. We are not just waiting for a discovery, we are waiting for an answer. Not an ambiguous signal or a tantalizing hint, but an actual answer to a question that humanity has been asking, in various forms, since long before space exploration was technically possible. The question of whether we are alone in the universe, or at least alone in the history of our solar system, is one of the oldest and deepest questions in human intellectual life. And for the first time, we have a concrete path to answering it, a sequence of scientific steps: sample collection, sample return, laboratory analysis that leads from where we are now to a level of understanding that would allow a definitive scientific statement. The answer, when it comes, will be received by a world that has already been prepared for it by the discovery of Chayava Falls. The scientific community's careful, cautious, rigorous engagement with the leopard spots and their chemical context has already shifted the terms of public and scientific discourse. The question is no longer whether we should take the possibility of ancient Martian life seriously. The evidence demands that we do. The question now is what the evidence, fully analyzed, will ultimately say. If the answer is yes, if the laboratory analysis of returned samples confirms beyond reasonable scientific doubt that the features inside Chayava Falls are the preserved chemical remnants of ancient microbial life, the consequences will cascade across every domain of human thought. And activity. The scientific implications alone are staggering. A second independent origin of life in the solar system would transform our understanding of the origin of life itself, our assessment of the prevalence of life in the universe, and our theoretical frameworks for the relationship between planetary chemistry and biology. It would open new fields of research and close old debates that have persisted for decades. The philosophical and cultural implications would be equally profound. Every major human tradition, religious, philosophical, scientific, artistic, would have to contend with the reality of a universe that is, at minimum, biologically plural. The sense of human uniqueness and cosmic isolation that has shaped so much of our cultural and religious self-understanding would need to be revised. This revision would not be simple or uniform. It would play out differently across different cultural contexts and different belief systems, but it would be unavoidable. The knowledge that life arose on Mars, that the solar system we inhabit has hosted biology on more than one world, would become part of the foundational context within which human civilization understands itself. If the answer is no, if exhaustive laboratory analysis reveals that the features inside Chayava Falls, compelling as they appear, were produced by non-biological chemistry, the outcome is still scientifically valuable, even if emotionally deflating. It would mean that the specific combination of features that currently suggests biology has a non-biological explanation that we have not yet identified, and finding that explanation would advance our understanding of Martian geology and geochemistry. It would sharpen the tools and criteria that astrobiologists use to evaluate potential biosignatures, making future investigations more rigorous and more reliable. And it would focus attention on other samples, other locations, other lines of evidence that might speak more clearly to the question. The honest scientific assessment is that we do not yet know which of these outcomes the evidence will ultimately support. The data from Perseverance is suggestive and compelling. It is not conclusive. The history of science councils caution in the face of extraordinary claims, however well supported they appear on initial examination. The conclusion that Mars once harbored life is among the most extraordinary claims in the history of science And it will require an extraordinary standard of evidence before it can be accepted with the kind of confidence that allows it to be stated as established fact rather than provisional conclusion. But caution is not the same as dismissal. The evidence from Chayava Falls demands serious engagement, rigorous analysis, and sustained investment in the program of sample return that will allow that analysis to be conducted at the level required. The scientific community recognizes this. The space agencies and international partnerships involved in Mars exploration recognize this. And the broader public, which has followed the story of Mars exploration with genuine passion and genuine curiosity, deserves to be part of a conversation that is honest about both the significance of what has been found and the uncertainty that remains. We are at the beginning of the final chapter of a search that has lasted generations. The tools exist. The samples exist, sealed in titanium on the surface of another world. The laboratories wait. The scientists are ready. The question that has defined the aspirations of planetary science for more than half a century is closer to being answered than at any previous point in human history. Mars has been watching us search. It has watched our telescope scan its surface from afar, watched our first clumsy spacecraft fly past and return blurry images, watched our landers touch down and probe the soil with instruments not quite sensitive enough for the questions they were trying to answer. It has watched our rovers cross its plains and climb its slopes and drill into its rocks, getting closer and closer to the evidence it has been holding in silence for 3.5 billion years. And on a July morning in 2024, a small drill on a robot the size of a car broke through the surface of a rock called Chayava Falls, and the planet showed us something it had been keeping for a very long time. Dark spots against a pale background. The chemical signature of ancient chemistry, a pattern that the entire weight of Earth's biological science says is the trace of life. Whether that is what it truly is, whether those small dark circles are indeed the empty plates of ancient microbial feasts, the chemical shadows of organisms that lived and breathed and reproduced in a Martian lake 3.5 billion years ago, is a question that the next years of scientific investigation will work to answer. It will not be answered easily or quickly. It will require the most careful, most rigorous, most methodologically sophisticated science that our civilization can bring to bear. It will require the return of samples across hundreds of millions of miles of space. It will require collaboration across nations and disciplines and generations of researchers. It will require the full weight of human curiosity and human capability directed at a question of human magnitude. But it will be answered. That is perhaps the most important thing to understand about where we stand. This is not an open question in the sense of being permanently unanswerable. It is an open question in the sense of being actively and concretely in the process of being answered, with a specific scientific path laid out that leads from current uncertainty to future clarity. The universe has been generous with its hints. The same carbon chemistry that underlies life on Earth appears in meteorites and interstellar clouds and the atmospheres of gas giant planets. The same amino acids that build proteins in every living cell on Earth are found in ancient meteorites that have spent billions of years traveling through interstellar space. The same molecules that store and transmit genetic information in terrestrial organisms can be synthesized under conditions that existed on the early Earth and presumably on the early Mars. Chemistry, the universe seems to be telling us, wants to become complex. It wants to organize itself into structures of increasing intricacy. It wants, perhaps, to become alive. Whether it succeeded on Mars, whether the chemistry of the ancient red planet crossed the threshold from complexity to biology in the warm, wet environments that existed 3.5 billion years ago, is the question that a rock called Chayava Falls has brought into sharp and urgent focus. It is a question that the next chapter of Mars exploration is positioned to answer. And it is a question whose answer, whatever it proves to be, will mark one of the most significant moments in the long history of humanity's attempt to understand the universe it inhabits. We have looked up at Mars for thousands of years. We have wondered, dreamed, speculated, theorized, and eventually built the machines and the knowledge required to go there and look directly. We have crossed the void, landed on another world, and drilled into its ancient rocks. We have found something that looks, to the best eyes and best instruments we have, like the trace of life. Now we wait and we work. And we push forward toward the moment when the uncertainty resolves, when the evidence is complete enough, and the analysis rigorous enough, and the scientific consensus clear enough, to say with the confidence that knowledge requires what we have found, and what it means for us, and what it means for the universe that made us. The red planet is no longer silent. It is speaking, in the language of chemistry and geology, across 3.5 billion years of time. We are learning, slowly and carefully, and with extraordinary effort, how to listen. And what it appears to be saying, what the dark spots inside Chayava Falls appear to be whispering across the gulf of time, is something that we have always hoped, and never quite dared to believe, might be true. We were not the first.